Good evening, and thanks for joining tonight's TI Technology webinar, hosted by Texas Instruments. For tonight, we're going to look at some pretty decent mathematically upper-level stuff, some sequences and series, and maybe how TI Technology can help us with those. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. And tonight we're lucky to be joined by our two panelists, Kim Thomas and Dennis Wilson. Kim is a nationally board certified teacher in her 27th year of teaching high school mathematics. This year, Kim is teaching AP, BC Calculus, and Geometry at Moon Valley High School. She has 6 years of experience as an AP Calculus reader. In addition to teaching, Kim works with math teachers in a variety of professional development environments, promoting student exploration, understanding, communication, and engagement. Kim, it's great to have you with us.
It is wonderful to be here this evening.
And for the last 24 years, Dennis has been teaching at Landmark Christian School in Fairburn, Georgia. He has taught every level of math offered at Landmark, from 5th grade all the way to multivariable calculus 2. In 2012, Dennis presented annually at multiple conferences on technology use in the math classroom. He served as an AP reader as well for calculus for the past 5 years and formerly served as the president of the Georgia Association of AP Math Teachers. So Dennis, we're excited to have you with us as well.
Thanks, Mike. I'm really excited to be here.
And Dennis, at this point, if you don't mind, can you talk through some agenda points for tonight?
Well, we began already with our welcome and introductions, and what we'd like to do tonight is to look at what is probably an underused feature on the TI-84 and the TI-Nspire, the sequence mode. In fact, it might even be unknown to some of you. We're going to look at this feature on both platforms by taking a look at the instruction of sequences across the entire curriculum. So if you're an Algebra 1 teacher, we'll be exploring that, geometry, all the way up to calculus. And so the things that we're going to look at is how to plot a sequence, how to do recursive geometric sequences, how to find and plot partial sums with the calculator, and then we'll even top it off with the infinite series. And when it's all finished, we're going to have a drawing, and one lucky person is going to win the handheld of their choice.
Awesome. I also heard, I don't want to spoil anything, but I heard there's going to be a cake. That's why I'm here. So, Kim, at this point, would you discuss through the expected outcomes?
So by the end of the video, we're going to have everybody, we would hope that you can plot an explicit sequence on a TI handheld to solve a problem. We would hope that we can plot a recursive sequence on a TI handheld to solve a problem. I can work with partial sums on a TI handheld to solve problems, and I can explore the harmonic series using a TI handheld.
Awesome. Thanks, Kim. Tonight we'll be using the chat window to send general messages, and as a reminder, this session is being recorded. If you have any questions for Kim or Dennis, feel free to use the Q&A window on the right side of your screen for those questions. At this point, let's get the party started. Dennis, it is all yours. Feel free to share your screen. Hey, Dennis, I think you're muted. I was going to let you go for another 5 minutes, but I figured that might not be good.
Yeah, no, I'm sorry. Oh,
thanks.
I knew it was happening. I was just playing the game. No. So I'm starting in the TI SmartView emulator, and I have reset the emulator. So I'm in a familiar state that most calculators are in. And just a little confession to start with. When I first started teaching, I was teaching chemistry, and my students would come and their calculators wouldn't do what it needed to do. And I was like, let's just reset it. And so this is kind of the familiar place for me from the beginning of my career with the TI-83. But what I want to do is, before we get into the sequence mode, I want to just kind of take a tour of what we're familiar with. Okay, so I'm going to clear this screen. The XT theta button, which is right here. Okay, when I press that in the default mode, I get an X on my screen. When I press alpha F4, I get the list of the Y functions from Y1 down to Y0. When I press window, I get the X min, X max scale, same thing for the Y, and I have some values down here. So pay attention to these values because they're going to disappear in a second. And then we are hopefully used to the format window, which here on the 84 CE gives us some great new features like the grid on with the dots and the lines. And we're going to get something else there when we switch to sequence mode. So to switch our mode, I'm going to press the mode key here on my calculator, and I'm going to go down to the line where function is highlighted. And you see on this line there are 4 different modes. There's function, parametric, polar, and sequence. These correspond to the 4 letters on this key next to the alpha key: X, T, theta, N. X for function, T for parametric, theta for polar, and N for sequence. So I'm going to push over so that sequence is flashing, and I will press enter. And so now my calculator is in sequence mode, and I can press second, quit, and it takes me home. So let me just start. I'll press XTN theta now that I'm in sequence mode, and notice my calculator is no longer giving me an X value. It's giving me N as the variable when I press this key. The next thing I want to look at is when I press window, I have new options here in my window set. I have an Nmin, an Nmax. I have a plot start and a plot step. Under that, you'll see I have Xmin and Xmax just like I did in the window before, but there's none of the stuff that I have down at the bottom that I had in function mode. Okay. The one other thing we'll look at before we hit in the biggest difference is the format window. When I press alpha zoom second zoom for format, you'll see I have another line here across the top. Right now I'm in time, and that's what we'll be doing at first. Later we'll make use of this UV plot and we'll understand VW and UW. We won't hit that web mode tonight. So the biggest difference is when I press the Y equals key. So what are some differences that you guys are seeing immediately when you see when I press this Y equals key, those of you who are 84 users out there? Okay, so we're not seeing Y equals, Joshua says. So I'm seeing U, V, and W. I have only 3 options for functions instead of the 10 options of Y functions of X. I now have U, V, and W as functions of N. You can see across the top, I've got sequence types: sequence of N, sequence of N plus 1, sequence of N plus 2. Jesse points out, we're going to look at the first 2 and we'll make mention of the third one later. And then the Nmin here is equal to 1. Okay, this Nmin is the same Nmin we saw in Windows. I can change it here, or I can change it in my window settings, but we'll see why it's important to have it on this screen later tonight. So 3 functions, and the one other thing I'd point out is right here. Right before the U, you'll notice that it's a discrete plot. By default, in function mode, we get a continuous plot where it connects all the values that are plotted. Here we're going to get a discrete plot because the domain of each of these functions is not going to be the set of real numbers, but instead it's going to be a set of integers. So, like I said, we're going to be looking at this in terms of some problems. And so this is just a sample from an activity on arithmetic sequences that is going to be available for download after the webinar is finished. But Clark Kent arrives in Metropolis without any money, and he's hired at the Daily Planet, where Perry White pays him at a constant rate of $25 per day for each day he works. And so students would fill out the table, and what we're trying to get the idea of is that we're increasing by that common difference that we teach with the arithmetic sequence. Okay, when I do this, I'm trying to avoid non-integer values. I don't want to have students running into difficulties because they have their proportional reasoning skills aren't fully developed. So we're going to plot this sequence. So what I want you to do is just take a look, okay? My input is going to be these integers at the top, the day's work. My output, my function, is going to be dollars. So when I go here, I want to plot this as UN as an explicit sequence. So what function might I use for this sequence of values? What function might get me the value I need? So I'm going to do 25 times n, and again, thanks Jay, 25, and then I'm going to multiply by n, and this xt theta n key gives me that n. So next thing I'm going to decide is how many values I want to plot. Okay, before I go to my window, I want to have an appropriate window to see, because right now if I press graph, I get that nice zoom standard window and I don't see anything. And so if I'm not thoughtful about the mathematics, I might think my calculator's broken. So it's always good to decide what your window is first. So I'm going to press window, and let's just look at the first week that Clark is going to work at the paper. So Nmin would be 1. He works 1. That's the first day he works. And I'm going to set Nmax to 7. So we'll see the first week. Okay. On the horizontal axis, that's the Xmin, Xmax. I'm just going to start at 0. And I'm going to go up to 7 so I can see that first week. So Ymin, he's definitely not going to owe any money when he starts. So we'll start at 0. And what would be a good Y max? Well, here kids might, they might struggle with the multiplication. They're not quite sure how much money he's going to have in that particular amount of time, but they have a calculator in their hand. And when I first started using the 84, what I would do is I'd quit, go home, do a calculation, and then I'd come back and put it in this window. I don't know if you've done this, but
I'm
anything,
guilty.
you're guilty, okay.
I'm guilty. I've done that.
I'm just going to put the calculation, 7 times 25, okay, which Jay says is in the area of 180, which it is, but I'm just going to go 7 times 25, and my calculator, if I go to that next line, goes ahead and does the calculation there. And so now I'm ready to graph. And so I've got these 1, 2, 3, 4, 5, 6, 7 points there. And so what I'm interested in is my students seeing the relationship between these points plotted on the graph. And so when we talk about this relationship, I might get the words, oh, they form a line. And, I will take that, but I'll try to get it a little bit more, because we're not seeing a line. We're seeing 7 discrete points, and maybe we get the word collinear out of them. I doubt it. I might have to mention it, but they all 7 points fall on a line. I might get students talking about the fact that the output is directly proportional, Josh says. So getting students to see this behavior and to talk about this behavior is really what I'm wanting from them. Now, when I go to trace these values, in the function menu, it traces by your window settings. So based on how wide your window is and how many pixels it has, it decides on that trace step. But here, and when I trace in sequence mode, I'm hitting each point individually. Notice that it's tracing those n values, and the n values happen to be the same as those x values right now, but it takes me to each point discretely. Okay? So now what I want to do is put in a second problem that's related to the first. Okay? Clark Kent comes to work, and every day he writes 3 stories for the Daily Planet. So we have another function that I want to put in for v. So I'm going to come to my y equals, and I'm going to go down, and for vn, I'm going to press 3n for my function. And then when I press graph, I once again get 7 discrete points that all lie on the same line. I see that directly proportional behavior that Josh mentioned. I've got one function that's increasing more. And again, we're having a discussion about what the students see. At this point with my students, I'm not even talking about the word slope. I don't want to confuse the issue of that linear function that my students really, I'm using this as an introduction to that. I might use steepness, but unless they bring that word in slope, I'm going to try to avoid it so that when I introduce it later, we can have that conversation and its meaning in the mathematics. But we definitely have two different steepnesses. So once we've had that conversation, I want to talk about the fact that both the amount of money Clark is getting paid and the number of stories he's writing are both related to the number of days he worked. And because they're both related to that same input, they're related to they're related to each other. So every time he writes 3 stories, he's going to get $25. He writes 3 more stories, he'll get another $25. And so what's nice in sequence mode is I'm going to plot one of these sequences as a function of the other. Remember I said in second zoom for format, we were going to look at this top line. So right now it's on time. And what time does is it always graphs in on that horizontal axis. But I'm going to move over here to UV and hit enter. When UV is selected, U is going to be my horizontal axis and V is going to be my vertical axis. So when I go to graph this now, wait, everything disappeared. What happened? I had 7 distinct points for both of them. But what's happening now is the x-axis is the amount of money I was getting paid. And then the y-axis is the number of stories I was writing. So I need to go back to my window, and I'm going to go back and because the x-axis was the number of the amount of money I was getting paid, I'm going to do 7 times 25 for the x max there. And then this was the amount of money I was getting paid. Well, I know that one's 21. I can do that math pretty quick without the calculator. And now when I graph it, there are my points. And of course, while I'm in there, I might want to set up my x scale and my y scale so that I can see how these values relate to each other. I could even then go to my format and turn on a grid. But what I like here now is that as I trace these points, it's going to trace the value of n, but notice now x and y. It's taking me to those x and y values that are plotted, but it's doing it at those discrete intervals. And I just want to mention that I think this is important for students, that when they're talking about math in context, really originally when they're first getting into algebra, that when they talk about math in context and we're talking about difference in x and difference in y, that we want to stick with these discrete values. Sometimes we get so like ingrained with like, what are the zeros? What is the slope? What is the value of the function at this point, that we miss the idea of what the math should be in context. And what I want my students to get from a linear function first is that the change in x, the difference in x, is a arithmetic sequence, and the difference in y is also an arithmetic sequence. So if I have a constant difference in x and a constant difference in y, I get this linear behavior that I see. Okay, and Jesse has a great question. Will zoom fit work as well? So I'm going to zoom fit real quick before I hand it over to Kim to show it on the Nspire. And zoom fit does a remarkable job of fitting these 7 points right into the screen. And what zoom fit is doing is it's going to fit the X window and the Y window based on whatever number of plots I have. So I only did a week, but if I did 31 days for n from 31 to 31, and then did zoom fit, it would fit all those plots. So zoom fit works really well It kind of is bothersome to me to use it originally on the arithmetic sequence because pretty much I'm almost always, if I'm only doing one type of plot, it's just going left to right, right across the screen.
It does
But
give the
as
inaccurate illusion that that might have a slope of 1.
it does. But as we move on and we see some of this other stuff, we'll see Zoom Fit kind of works pretty well for us as we explore more. So that said, I'm going to turn it over to Kim, who's going to show you the same um, same the same
Skills.
mode on the same skills on the TI-Nspire, but she's going to do this with a geometry problem.
All right. Share my screen here, and I am using a TI-Nspire. And so this is my TI-Nspire CX2. And I'm just kind of pretty much on this home screen right here. And so I'm going to do a brand new document. And just like Dennis, I'm going to go in and add a graph. And so when I do a graph the first time on the TI-Nspire, I do get this function graph basically in the Cartesian coordinate system. And what we want to do is we want to change that. So I don't have to go in and change my mode on my TI-Nspire. I just have to decide what type of plot I want to do. So in the TI-Nspire, if you hit Control and then Menu, it will ask you if you want to change this graph entry line. So this top line up here is your graph entry line, and we have these choices. We can do functions, we can do relations, there's all these equation templates in there. We have parametric graphing, we have polar graphing, we have scatter plots, we have sequences, and differential equations. And so for this evening, we're focusing in on sequences. So I'm going to select sequence. For the TI-Nspire, we have U1 of n. And we'll have our initial terms and how many terms that we want to do. And that's really all we need to work with. So if I were to go to a different plot, and so if I go down, now it's U2, and then it'll be U3, and then it'll be U4. So in the Nspire, I'm not going to have a UVW, I'm going to have U1, U2, U3, which follows the same type of setup that it did with functions where you had F1, F2, F3, and so on and so forth. So that's kind of our setup. Just to kind of compare the two, I'm not going to put one in there yet, so I'm going to hit escape. Let's go ahead and think about our situation we're going to deal with. So our geometry setup is that I would like to find the sum of the interior angles of a regular polygon by drawing the diagonals and counting the triangles. So as a geometry teacher, I have done this particular lesson different times of the year. I've pulled this lesson into pre-cal classes, and it just depends on what I want to do with it. As a geometry teacher, I really, really need my students to interact in with the shapes. And so I'm not going to provide them an electronic answer. I have a worksheet that I'm going to have them work out and draw in those triangles and then count them up. So I'm actually really doing this kinesthetically, pen the paper, kind of old school just to get what's going on. But this is the idea. So I have a regular triangle, which would be an equilateral triangle. Can I draw any diagonals in there? So, you know, my beginning geometry kids, that's a big discussion to even kind of figure out what's going on there. So what's the sum of the interior angles of a triangle? 180. Then we'll go to our regular quadrilateral, which is a square. And can I draw some diagonals in there? So again, with all my students, they're kind of learning what is a diagonal, how does that work? And so I'm going to just go ahead and draw in the one diagonal. And that's when we really do make sure that we have adjusted our expectation and we are not drawing just diagonals in, but that we're drawing in our diagonals from one point. And then we will do that again with our pentagon. And from there, we can see that we have 1, 2 diagonals. And every time I've done this physically with students, then I kind of have to go back and we have to start coloring in triangles. So this will get different shapes in there. We'll get different colors in there. And so for that pentagon, there's 3 triangles. And then we'll do the hexagon. And there is a worksheet that is in the materials when you download the materials for this webinar that has these shapes to where students could draw in those diagonals with a straight edge, just because sometimes it's nice to have that resource there. And that's just kind of how I chose to do that at this point. Now, if I'm up in the front of the classroom, I'm building these shapes, we're drawing these triangles, students are working in groups doing that, however you're going to manage your classroom with that. But it's only useful if we collect the data. So from this concept, we're collecting this data. I have these regular polygons, I have these number of sides, we're filling that out, and we're counting triangles up there, and then we're kind of connecting that piece where the sum of the interior angles is how many triangles there are. So when there's 2 triangles, I had 360. When there's 3 triangles, 540. Where did that come from? And I want my students to build the fact that if I have an input of the number of sides, if I take 2 less than that, which was the number of triangles that resulted from drawing in the diagonals, I take that and I multiply it by 180. And that's the sequence that I want to plot with my students. So if they don't already know this formula, I want to build that concept with them. But I also want to look at it from a sequential point of view because especially on polygons, we don't have 2.5 sides. That's not going to happen. So it really fits in nicely there. So we're going to go back to our Nspire and we're going to plot that. So I'm going to press tab. Here's my U1 because I already changed that. And this is where we're going to go ahead and type in what we have. And so it's going to be n times, I'm sorry, it's not n times that. It's 180 times n minus 2. And for this particular sequence, I don't really want 99 shapes. So I'm going to go ahead and change this to 10. So the n right here is telling me, what do you want to start at? I want to start at an input of 1. Oh, wait, do we want to start at an input of 1? And so what's really nice about this geometry here is that you're right. We don't want to start at 1. We want to start at 3 because our first polygon had 3 sides. So now we actually are really even more in control of what we're looking at our sequence. And we're not just straight up looking at a continuous line. We're actually really thinking about purposely how this is set up. We're going to press enter and we don't see anything. So again, we want to make sure that we manage our window and look at some things. And I can go into menu right now. I can check out my window right here and I have my window settings and I have all the same different things that we had before. I'm going to go ahead and look at just window settings first. In our window settings, we really are just adjusting our X's and our Y's. So we don't have to adjust for the other pieces because that was part of the sequence that we wrote right here. So the question is up there, could we use Zoom Fit again? And that might have been for the last one, but I'm going to go ahead and use Zoom Fit here because I'm kind of an anti-Zoom Fit person. And I've been playing with it, working on this webinar, and I really like it for sequences because it's so easy. Like, there it is. But at the same time, there's some things I don't like about it, but it's so easy to change it on my TI-Nspire that I'm okay with it. So when I zoom fit, I'm like, there it is. And there's our, looks like there's a diagonal across the screen. I know it's not 45 degrees because this is a rectangle, but my Nspire, it's really easy to move that label. And for me, I really do want to kind of see a little bit more going on there. So I could really grab the screen and adjust some things. So I really did just mess up my zoom fit. But I can take this number and I can double click on it. Like, this is my favorite way to change a window. And so I know that I only went out to 10. So I'm going to just change that to 12 right now. And I'm pressing my tab key. I'm not pressing enter. I'm pressing my tab key, and what that does is that kind of moves me around the screen. It's a little hidden, but now I can see that it's right there at my Y min. I'm going to change that to -1.
That tab key, that's kind of like the big difference moving from the 84 to the Nspire, isn't it? Like, instead of enter, you're tabbing everywhere.
Yes, and I call it like going around the world. I kind of think of it like as a little basketball game. And then up here, I've never tried this, Dennis, but have you ever tried to type in numbers before? Like
Type in
multiplying?
numbers? I have.
You have? So it's going to work?
Yes, it's going to work. It's a calculator.
There we go. So if I did 180 times, I'm going to go with 10. I'm going to go with larger. I know it should be 8. Wow, it works. And that is the first time I've done that. So thank you for reminding me of that. I've done that in menus, but I've never really done that on the screen. And then on the Nspire, kind of a little annoying that I'm counting by 0.5s. I'm going to change that. And because I'm on my computer software, it's easy to do that right there and change that to 0.1s. But we have that beautiful graph. And what's super, super powerful with this is the fact that I can go and trace it. So again, on the Nspire, we hit menu and trace, and we're going to hit graph trace. And now you can see what's different about this particular plot is I have my ends. So at n equals 3, my input of 3 sides, I have a sum of 180 degrees. At n equals 4. And then don't forget that you can jump around. So I can type in 6 and hit enter, and I can see what happens at 6 sides. I could type in 10 and hit enter and see what happens there. And now I've I have some large numbers here, so I have some scientific notation going on. And so that is something that we kind of have to contend with. The other thing about the Nspire that I do like, especially with these large numbers, is that I don't have to trace. So I could actually just hit Control T. T is for table. Table starts with T, Control T. And then I had those inputs and those numbers there as well. So if I really wanted to see 1440 without the scientific notation, that's one way to do it until it gets really, really, really large. And what the other piece is that, you know, my students built a table, so they have these numbers in front of them, so they might not need that there unless they really wanted confirmation. But if we didn't start with the table on paper, now I have a table to connect back those values, and doing those multiple representations so easily on the fly, I think is really, really important. So that's the first piece. Do we have any questions there? I think we're looking pretty good. And I want to do the same thing that what we did with the superheroes and paying and writing stories. And so I added another piece to this, and this is not something that I would do immediately in my geometry classroom, even though the concept does kind of come into next. So I talked about regular polygons for this, not because the polygon needs to be regular in order to find the sum of the interior angles. But I talked about a regular polygon because I want to now know what is the measure of an interior angle. If I happen to know the sum of the interiors, can I go find one of them? And so building that idea, okay, I know for a triangle, they add up to 180. If there's 3 of them and they're all the same, they all must be 60. And for a quadrilateral, again, they add up to 360. If they're all the same, they have to be 90 each. And for my pentagon. So I'm building the same idea with my students, saying, okay, if I have the number of sides, how am I getting that interior angle? And hopefully they're realizing that we're taking that sum, that 180 times n minus 2, and we're dividing it by the number of sides in that particular polygon. And so that's the second sequence that I want to plot. So I'm going to go back to my plot here, and on the Nspire, I'm going to just press tab. And so there's my U2. And I could do this a bunch of different ways, but I'm going to just kind of do it straight directly. So I'm going to use that control divide to get my fraction here. And so I had 180 times n minus 2, and I'm going to divide that by n. And again, for these polygons, I need to start when n equals 3, and I don't want a ton of them, so I'm just going to go up to 10 right now and kind of keep it in that window right there, just like we looked at the week for Clark Kent. And there it is. And that's a little bit different. Now, it's a little, it might look linear. Is it linear? Does anybody know? Any ideas? And so I'm kind of curious about it. So what I'm going to do is I'm just going to go ahead, and we have confirmation it's not linear. So I'm going to go ahead and add a page right here and do a graph. And a little frustrating, but I still have to do control menu, and I have to change each graph back into my sequence here. And I'm going to go back up to U2, and then I'm going to press enter on that. And I can kind of see that graph, and then I'm going to be lazy because it's just so pretty. I'm going to hit window zoom and we're going to do zoom fit. And wow, definitely not linear. Now, what didn't I take care of before I did that so quickly?
Why do you have so many points?
Yeah, what, like, I thought I just graphed the same thing, right? And so if we go back in and we look at what I plotted, I copied over U2, but because I opened up a new screen, the ends reset in the sense that the end step was still 1, that's the default, but it reset to the default. So I need to change this to a 3 if I wanted to start with my triangle, because it's doing math. The math is correct, but is it correct for the situation? No. And then I want to change this to 10. And so now I can go back and do menu, window zoom, zoom fit. And now I can see that it's a little bit, it's definitely curving there. And I think really if we even look at the table again, we can now start talking about those linear relationships. Again, on the table, it's going to calculate any integer input. That might not be what I defined, but that's definitely something you want to think about. What I do like about the table is that even though I defined my graph for 10 points, it is going on. So I can go and look at, oh, wow, for a 20 gon, it's going to be 162 each. And then we can talk about what happens as we get infinitely many more sides. And that conversation is much more accessible by having the calculator do all of this talking. And yeah, it like looking for that horizontal asymptote. So I bring this geometry back in when I'm teaching pre-cal, just because I want to review geometry and I love geometry as a geometry teacher, but it is something that we can talk about those other concepts. And algebra 2 is definitely where it is. Now we want to put these two together, just like we did with the other ones. So I'm going to go ahead and hit another page right now. I'm going to do another graph. I'm going to hit Control Menu, and I'm going to change my graph entry line, and I'm going to go back to sequence. And when I do this, again, we kind of talked about this, these might be hidden features for all of us. I have like glanced over that custom forever and never really bothered to think about what I could possibly use for it. So on the Nspire, I'm going to pick custom instead of doing this UV piece and the web and all of the VU and all those other stuff. So now I get a plot, and what am I going to put into X1? Well, I am going to go ahead and press the variable key. And I need to decide, do I want to have along my x-axis, do I want to have the total sum, or do I want to have the individual angles? And I'm going to choose the individual angles. So I'm going to do U2. And so this, again, I would be very clear in the classroom what U2 is representing. And then for Y1, again, and I could type this in, I could type in U1. Notice how it just automatically turns bold, and type it in. On a handheld, it's much, much easier to do this with using the variable key. And I'm going to make sure that I do this correctly. So my polygons start with 3 sides. I'm only going to go ahead and look at 10 of them. And wow, it's missing again because I didn't really deal with my window zoom. So I'm going to go ahead and do that and zoom fit. And now we have this relationship going on here. So there's my data points. I can see that this is definitely not a linear relationship, but that zoom fit did kind of put the points in the corner. And really, it's the conversation that I want to have with trace. So if I'm looking at graph trace here, when I have a pentagon, the interior, when I have a regular pentagon, excuse me, when I have a regular pentagon, that interior angle is 108. The sum of those angles is 540. And so this piece, we just really wanted to make sure to model it, how to do it on both technologies. I don't know if I would do all of this in class, but the fact that I can is pretty impressive. Maybe I have it set up for my students and we talk about it from there. And that is our geometry example. Isn't it time for cake?
I think it's time for cake.
It's time for
Time
cake.
for a
Like
snack.
I've been thinking about cake all day. This really has been like, wanted to have some cake. So I am going to, there you go. It is
Okay.
yours to share some cake.
Awesome. So the next activity I want to look at that we're going to do for recursive sequences is this, whoops, went one too soon, is an activity I call half now, half later. And the reason I call it half now, half later is because there's a great video by Math Theater on YouTube of two teachers taking a trip, and they have a cake and they eat half now and save half for later. But the idea is each time we take a slice of cake, we're eating half of what's left. And so here is a nice little picture of it. And so you can see we start with the full cake blue, and we just take half of what's left every time we take a bite. And so what we want to do is look at plotting the size of the piece, but we're also going to look at plotting how much total cake is eaten, because that represents a sequence as well. So while Kim was demonstrating the Nspire, I went ahead and reset my calculator. So I've got a blank slate, and I went ahead and went into the sequence mode. Remember, we went into sequence mode by pressing the mode key and highlighting sequence and pressing enter. So I'm going to go in to my y equals, and I'm going to make some changes. The first thing I'm going to change is the sequence type. So previously, when we were doing an explicit sequence, I wanted to only, everything was based on n, so I just did sequence of n. Now watch what happens when I move over to sequence of n plus 1 and press enter. So what happened is the input of u, v, and w for my functions has changed. Now I'm making a function u of n plus 1, and so this is useful for us to do recursive, because now I can define u of n plus 1 as something of u of n, okay? So if you were doing Fibonacci, maybe you need two previous values, and so sequence of n plus 2 would be useful. So I'm going to change the n min here to 0, and I'll talk about why in a second, but I'm going to change n min to 0, and the key idea here is that my cake is going to be, I'm going to always eat half the cake. So it's always going to be half of what I had to start with. So I'm going to put in 1/2 times u sub n. Now I'm going to use a feature that's might be unknown if you're new to the 84 plus CE, but you might notice on my emulator now, right above the xt theta n key is a template for the fraction. So if I press alpha xt theta n, I get a fraction template. Now, if you're on the 84 plus silver edition, then you're going to be able to access that by pressing alpha y equals to get that fraction template. But I like that it's really quick and easy right there on the key now, one less keystroke, and it's visible for the students to grab. And I'm going to use this fraction template, and I'll talk about why I think it's important to use it here in terms of the behavior of the 84, but I'm going to make this 1/2. And what I want to do is multiply it times u sub n. So what are ways that I would get u here in the window? So one of the things I might do is look at this blue u above 7. Okay, so if I pressed second 7, it would give me that u, and I could open up a set of parentheses and type in n plus, I'm sorry, 1/2 n. I'm ahead on my notes. Okay, so 1/2 times u sub n. And I'm going to go down, and we'll look at another way to enter that u in a second, but I've got to put the initial value here. Okay, so when it goes to find u sub 1, it's going to look for, well, what was u sub 0, and I've got to tell it. So I decide how much cake I'm eating by the size of the initial piece. I've got a whole cake to start with. So I'm going to go ahead and I'm going to set my window. I'm going to look at the first 10 pieces, and then those 10 pieces are my horizontal axis. And because I never have more than one entire cake, my the size of my piece will never be bigger than 1. So I'm going 0 to 1 in the y. Now when I press graph, I have this nice exponential decay here. And what I like is that when I trace this now, and it traces through the n values, watch those y values. Those y values are getting expressed as a ratio of two integers. This only happens if I insert 1/2 using the fraction template. If I had done 1 divided by 2, these would be decimal approximations for these rational numbers, but I like that it's really clear to the student what's happening. Now earlier Kim showed the table with her, so let's take a look at the table. Before I sit at the table, I'll set it, and you can see that the table setup is exactly the same in function mode, looks exactly the same in function mode as it does in sequence mode. The only difference is the table start and the difference in the table are for the values of n and not for the values of x. So when I go to second graph for the table, there are those values that I see. And once again, because I put that fraction template in there, I'm getting fractional values at least until the calculator's like, okay, I'm done with that. But the students get to see it, and those are values they're all familiar with if they ever played 2048. So that is the size of each piece. What I'd like to do now is to look at taking a partial sum. So real quick, I'm going to go back to y equals, and I'm going to do the partial sum here in V. And so what this partial sum is going to be is it's going to take the function, it's going to add whatever size the cake piece is for n plus 1 and add it to what it had before. So this is there's great connections here to make with computer science if your kids have done some coding of having a counter that increments every time it goes in. But here's the other way I can get the functions. I can press alpha trace, and before we saw those were y1, y2 all the way to y0. Now I've got the values u, v, w, and so forth. So what I'm going to do is I'm going to do u sub n, but really what I want there is u of n plus 1. And then I'm going to add it to the previous value of v. So alpha trace again to get that previous value of v. And then I got to start with how much cake I ate in the very beginning. So I'm going to press 0 because I didn't eat any cake. And so this is now going to add up how much cake I started with, and then it'll add the first piece. So it'll add a half, and then it'll add a fourth, and then it'll add the eighth. I got asked if you could use the vars menu as well. So when I go to yvars, you'll notice that the sequences aren't there. And the reason the sequences aren't there is because they put them on the keys. There's only 3 of them. And so 7, 8, 9 is the way that you reach that. And so Jay's saying, hey, this is the sum of a geometric sequence. So I said, for a second graph. Nope. Ooh. I paused it. Okay. Sorry. All right, so I went to the table. I think it was having trouble with all those fractions. But if I go to the graph, there's my cake size pieces, and we can see that it's leveling off. And right here, kids are starting to get a glimpse of that infinite series, that we can add an infinite number of terms together and get a finite value. So I'm going to try to turn this over to Kim real quick so she can do a similar thing on the Nspire.
Okay.
And Jay's right, that sum will be 1. My kids will argue with me that it never gets to 1, but it's an infinite sum.
And what a great thing for them to explore there. All right, so we're going to go here, sharing back here at mine. And so because I'm on my TI-Nspire, I'm not going to reset my TI-Nspire. What I'm going to do is I'm going to press the dock button. And when I dock, I'm going to insert a new problem. So this starts me over at a brand new problem right here. And do you think we have enough time to do the cake and?
Why don't you just go ahead and do the harmonic?
Let's do that. Okay, so we're going to still
And you
go to
can,
graph, right?
yeah, while she goes to graph, I'll just mention that it's really easy to do recursive on the Nspire because you're just typing the functions. You have the U1, U2, U3. It's really easy to get those values and do recursive, but I think she's right. We should do some harmonic.
So not the harmonic series. Actually, I don't even know if this really has a number, but what we're talking about is we're taking terms and we're going to do 1 divided by n. And I'm just going to put 1 divided by n here for us to kind of get what we're doing with this. So I would do 1 divided by 1, 1 divided by 2, 1 divided by 3, and that would be my sequence. And I'm going to go ahead and look at 99 terms here. And I start with this at some point in time with my students, and just so that they can kind of see it's approaching the x-axis at that point in time. Again, on our Nspire, we can change this pretty easy. I don't even need to see negatives there, so I'm just going to type in that 0. And what I love on the Nspire though too is when I'm on a handheld, I can grab this axis and I'm holding down the shift key and I can just move the x-axis and see that approachment. So I think that, to me, that's a really important visual. And I know that I model that for my students and I said, don't worry about doing it on your handhelds unless you have to. Some of them can, but just for them to see all of those and see that dynamically change, which I think is pretty cool. But we want to talk about the series. So I'm going to go ahead and add a page. And I'm going to do another graph. And I'm going to change my control menu. And so by the end of this, we definitely get that pattern and we're going to do a sequence. And I want to add that up. And I could do this a bunch of different ways. What I'm going to do is I'm going to kind of take the lazy way out and I'm going to go ahead and use Sigma because I'm going to add up each of these terms. And so I'm going to select Sigma. And how I set this up is I'm going to say that I'm going to let n start at 1. And I'm going to go to n. And I want to use that sequence, which was 1 divided by n. And we also have on the Nspire above that control divide. I can do that 1 divided by n. It's not going to give me really cool things like the 84. And then my initial terms. So if I'm thinking through summation, if I put in a 1, I'm going to add in 1. And then when I put in a 2, that's 1/2. So it'll be 1 plus 1/2 and so on and so forth. So at this point, Dennis is going to tell me how many steps we want.
So let's just go with the steps are good.
Okay.
But what I want is a window that goes from 0 to 8. So we'll see the first 8 terms, and then y 0 to 3.
Okay. So
So
my
0 to
window
3 and
setting,
0 to 8 and x.
count by 1, and then our y's were 0 to 3.
0 to 3. Yes.
And I'm going to go ahead and count by 1 there.
And
I'm going
so
to hit OK.
when you're a calculus teacher, convincing students that this sequence diverges, that it continues to grow without bound, is one of the things that you really want to do. And so, like, I play a game with my students. Like, it's not quite to 3, and at this point, we're adding an 8th. The next term's a 9th. The next term's a 10th. How high do you think it will go? And maybe a student will say, I think it'll go to 3.5. So I'll change the y value right there on the window to 3.5. Oh, it looks like it might not get to 3.5, but then I'll double the x value. So I'll go to 16.
Ooh.
Ooh, it looks like it's on its way. So a student say, well, maybe it won't get to 4. And so we'll go to 4. It's like, okay, go to 4. And then I'll double that value to 32. And every time they go up a half, every time they go up to half, I just double the value. And then we'll look at it numerically that when I add a third and a fourth, that's going to be well, I group the terms, and if you've taught calculus, you can see you can get a half out of every next set of terms. Every time you double a term, it's going to be less than a half. And because of that, yeah, you guys can continue to add a half infinitely, but how many times can I double it? I can also do that infinitely.
That is pretty cool right there.
Yeah.
That's where I need the sideboard with all of that little writing over there.
Yes.
Which I think is really kind of cool. And, and I didn't do this, but I know when I practiced this, I really thought that it was nice to go ahead and have the grid on while we were talking about looking at half more.
Yeah.
That was kind of nice, even though I know this isn't like necessarily a square grid, but it definitely did help to kind of get that conversation going, which I thought was great.
And if your kids have done AP Chem, like that looks like a logarithmic graph would like show that perfectly.
Yes.
Yeah.
Cool.
Well, I think
All
that's
righty.
us.
That is us. That
Mike, you
definitely
there?
is us.
I am. I just noticed in the Q&A, someone beat me to it. I was about to ask that in the follow-up survey that everyone lets me know if maybe there's something else that you would like to see, and we already got asked for a second part. So maybe Kim and Dennis, you guys can start thinking about what a part 2 might look like.
Oh, certainly.
Definitely.
So if there are any last-minute questions for Dennis or Kim, please try to get those asked. I know they'll do their best to try to get those questions answered. As Dennis mentioned earlier, one lucky winner tonight is going to receive a TI graphing calculator. And tonight's lucky winner is Joy Dowdy. So Joy, congratulations. We'll be in touch over email in a few days, but you'll be able to pick the TI graphing calculator of your choice. It's a big decision. Congratulations. To download a certificate of attendance, go and click the link in the chat window. Also listed is the link for the documents from tonight. If you're having issues with accessing these links, hang tight. You'll automatically get a follow-up email within a couple days. And that follow-up email can not only contain links to the certificate and the documents, but also to the recording as well. And if you're watching this on demand, please go ahead and copy that link into your favorite browser to receive your certificate. We always love hearing from you, so if you have any questions after the webinar, feel free to give us a call at 1-800-TI-CARES or drop us an email, ti-cares@ti.com. I already mentioned this part, but when you leave the webinar, you'll receive a survey, and your feedback really does guide us, not only on how Kim and Dennis did tonight, but also what we should focus on in the future. We really hope you share your thoughts in that post-webinar survey. So huge thanks to Kim and Dennis for putting everything together for tonight. Thanks so much.
Yeah, thank you. It was an awesome night, and I had a great time working with Kim on it.
Yeah, this was a great presentation, and I already see a couple concepts that we can add for part 2. So the group is definitely making some good suggestions for us too. So this has been fun.
Awesome. I can't wait to see that feedback. So thanks everyone for joining us. We hope to see you back online next week. Have a great night.